In this video, I have 4 examples that I want to go over that will utilize the Pythagorean theorem in some ways that you might not see right away. So for instance, in this example, it says find AB as a simplified radical. So the distance from A to B. In the next section, I'll show you how to use the distance formula, utilizing the points A and B, to find the distance between them, but if you want to use the Pythagorean theorem, you can also do that because they are closely related. So in order to find AB, we have to first form a right triangle between A and B. And it might not look like we have one at first, but if we create some lines here, and my artwork here isn't great, and my straight lines and things like that, but we can form a right triangle making AB the hypotenuse of this triangle. So this would be C, and then from my vertical line here, it is 7 units long, and this is 1 unit long. So when I look at my Pythagorean theorem, a squared plus b squared equals c squared, I would go 7 squared plus 1 squared equals c squared, and solve this like normal now. So 49 plus 1 equals c squared, or 50 equals c squared. And then remember, I have to square root both sides. So we have c equals the square root of 50, but they do want this to be a simplified radical, so I'm going to take the square root of 50 and break that down. Fastest way to do that is to use 25 and 2, and we know the square root of 25 comes out to 5. If you want to see the pair, there it is, 5 and 5. That gives us a regular 5, and the distance from A to B is 5 times the square root of 2 units, whatever those units may be. So that's one way that you can find the distance between 2 points on a coordinate plane. You can always form a right triangle and use the Pythagorean theorem. But like I said, in the next section, I'll show you how to use the distance formula. All right, so now moving on to something that's a little bit different. Let's say we have a square, and we know the diagonal of that square is 20, and then we know the 2 sides are x and x, or they are the same. So we know this is a right angle. 20 is my hypotenuse, so this is C, which would make my x's a and b, okay, in my formula. So a squared plus b squared equals c squared, or the x's are the legs of the triangle. 20 is the hypotenuse. And what we would do here is put in x for a, so x squared, and b is also x, they're the same length, plus x squared equals 20 squared. So here's where things get a little bit interesting. We're going to combine like terms on this side because I have 1x squared plus 1x squared, which is 2x squared. And that equals 20 times 20, or 400. Now before I do my square root on both sides, I'm going to divide both sides by 2. So now we have x squared equals 200. And now I can take my square root, and again we'll get a simplified radical. So x is going to equal the square root of 200, but we do want to break that down. I will go 2 and the square root of 100, and just to save time here, I know the square root of 100 comes out to 10. So this is 10 times the square root of 2. So x equals the 10 times the square root of 2, or 10 radical 2 units in length. That's how we would do that. What happens if we're given a triangle and they want the missing side? In this case, we can see the hypotenuse is missing, the C, and we have the 2 legs. But we can also see one of the legs is already in radical form. So what does that look like? Actually makes things a little bit easier. So I'm going to call A 6, and b will be square root of 12, or radical 12. So we've got 6 squared plus radical 12 squared equals c squared. So 6 to the second is 36. Now if I take square root or radical 12 and multiply them twice, so radical 12 times radical 12, I just get 12. You could get the square root of 144, but it's going to bring us right back to 12. So really, when you square a square root, the square and the root cancel, and you're just left with what's on the inside. So here we actually have then 48 equals c squared. And then we could simplify this radical once we take the square root of both sides. So take your 48 and break that down. Saving time, I will do 16 and 3, because 16 times 3 is 48. I know the square root of 16 is my pen. Stopped working there. So 4 square root 3 is how many units long that hypotenuse would be. All right, one more example utilizing this same method. Sometimes you're going to have a problem where they have used the Pythagorean theorem more than once. So in this particular example, they say find the value of s as a simplified radical. Well, s is here. So in order to figure that out, I'm first going to have to figure out what r is. So I'm going to look at this triangle first, and we can see that the hypotenuse of this triangle is r. My two legs are 1 and 1. So 1 squared plus 1 squared equals r squared. Or 1 plus 1 equals r squared. Or 2 equals r squared. And then I square root, and r equals the square root of 2. So now we have figured out what r is. So I'm going to write that in. So this is the square root of 2. And then I have another triangle that I can now work with. And it will be this one. So now the square root of 2 is a leg of the new triangle. So really, and now s is the hypotenuse. So I will have 1 squared plus square root of 2 squared equals now s squared. And we have 1 times 1, which is 1. The square root and the square will cancel, just like it did on the last example. So we'll have 2. And that's going to equal s squared. And then we add 3 equals s squared. Take our square roots, and we get the value of s as radical 3, and we cannot simplify that any further. So that is how we can utilize the Pythagorean theorem more than once. Now there are a lot of different ways that the Pythagorean theorem can be used, but just let it be known that if there's right triangles involved and they're wanting the distance of some sort of length of a triangle, that you're more than likely going to use the Pythagorean theorem. And sometimes, as in this example, you'll have to use it more than once. A lot of different situations you can run into, but these are just 4 different examples that you can run into.